This is the first of two short videos which will allow us to complete the unit on rotational motion. In the two videos, these are the anchoring concepts that we'll be concentrating on. The first one in the first video is going to be learning about what angular momentum is. We're going to look at angular momentum for both a point mass and an extended mass. And then in the second video, we're going to learn about conservation of angular momentum. Both of these videos will then help you prepare for the fourth learning objective, which will be tested on, which is dealing with the conservation of angular momentum. Okay, so what is angular momentum? As we've seen with a lot of our other values or terms that we've learned about in this unit, for all the translational quantities that we've learned up until now, there's a rotational equivalent. And so for angular momentum, as you might expect, it's related to regular momentum. Now, the relationship is kind of interesting. When we talk about angular momentum, and this is for a point mass, the point mass is assumed to have a momentum, p. So it has a mass and it has a velocity. And when we measure the angular momentum, what we're looking at is the angular momentum is measured relative to some origin or some point of some axis. So for instance, in this drawing, we're measuring the angular momentum of an object here that's moving with a momentum as shown relative to the origin of this 3D space. And so when we do that, what we're looking at is we're looking at the momentum but relative to a particular point. And we're going from the point we're interested in to where our object is, and so that becomes our radius vector, which is located right here. And then we take that radius vector and we cross it with our momentum vector. So in some cases, the momentum is due to the fact that this object might be moving in a rotational way. And so then it makes more sense to think about angular momentum, but we actually can calculate the angular momentum of an object even if it's moving in a straight line, because we're still doing so relative to a particular location where the presumable axis would go through. Now, you can notice that this is a cross product right here, so it means that we can talk about the magnitude of this vector, where we would take it as the magnitude of the angular momentum would be the magnitude of the radius vector and the momentum, and then times the sine of the angle theta. We might want to put the momentum and the sine of theta together, which then would mean we'd take the radius vector times the momentum that's perpendicular to it, or we could put the radius vector and the sine of theta together, and that would be the perpendicular radius to the momentum. Sort of like we did with torque, if you kind of want to make an analogy to that. In any case, this is how we calculate the angular momentum. I wanted to look at this example so we could just practice how we might do the calculation of angular momentum. This one's going to give us 3 different chances, because what we are being shown in this picture is there's 3 different masses, and we are given their velocities, and we can find their angular momentum because we can also determine their radius vector, which is going to go from the origin to where the masses are located. So let's do this for mass number 1. Mass number 1 has a mass of 2 kilograms. Now, what is its radius vector? Well, the radius vector would go from the origin to here, and we can actually write it in unit vector notation. If we just look at where it is, it's at minus 2x, so it's minus 2I, and then up 1 in the y direction, so that's plus j. So that's our radius vector. Our momentum vector is going to be our mass times our velocity, which would be 2. And then if we look at the velocity for this particular one, we say it's 4j. So that would be 8j. The angular momentum of mass number 1 will then just be r1 cross p1, which is going to be here. And what we're going to do is we're going to take this, this r and cross it with the momentum. So we have minus 2I plus j cross 8j, which would end up to be, if we do it bit by bit, we get minus 2I cross 8j plus j cross 8j. Now, this is where we can remember our little handy dandy. How do we do cross products of unit vectors? Remember, if we go around clockwise to do it, we get the next unit vector. And if we have to go backwards, we get the next vector that's counterclockwise, but we have a negative. So in here, I'm taking I cross j. So I cross j, the next vector is k. So that's going to be in the k direction. And then we have minus 2 times 8, which is minus 16. So the first little piece of this is minus 16k. And then j cross j, well, when you cross a vector with itself, you just get 0. So our end result is the angular momentum of mass 1 is minus 16k. So let's try another. So this will do mass 2. And that mass is 4 kilograms. R2, let's draw it. We go from here to here, is 4 units in the x direction and 1 unit up in the y direction. Its velocity times its mass is going to be 4, and then its velocity was 5I. So its momentum is 20I. And then if I do its angular momentum, I'd get 4I plus j cross 20I. So again, we're just using the definition of angular momentum, where it's r cross p or r cross mv, whatever makes you more comfortable to think about it. All right, so this, we could break it down, doing the distributive property, 4I cross 20I plus j cross 20I. This first term goes to 0 because you have I cross I, and when you cross a vector with itself, you get 0. And then we have j cross I. So let's look at our little circle again. We want to do j cross I, which actually means we have to go backwards. So j cross I, the next thing we come to is k, but we had to go counterclockwise, so it's minus k, and then we take 1 times 20. So this ends up to be minus 20k. That's our angular momentum for that one. And then we're just going to do one more. You can follow along and do this on your own. The third mass is just 1 kilogram. If we do like this, that's R3. R3 is actually 2I minus 2J. P3, which is M3V3, is just 1 times 3I. And then using that, what is our angular momentum? So we're going to again do the distributive property. We get 2I cross 3I, and then plus a minus 2J cross 3I. Again, we have an I cross I, that just gives us 0. We have a J cross an I, which is a minus K, and then we multiply it by a minus 2 times 3. So that time, our two negative signs cancel out, and our answer is 6K. Okay, so those are examples of calculating angular momentum for just a mass, a point mass at a particular location. It's this one was really heavily related to using the definition of a cross product. Of course, there could be other variations for the problem that you might run into. Now, another thing that we might ask ourselves is, as we learn about this angular momentum, we might say, is there a relationship between the angular momentum and the torque of an object? So what am I thinking about here? Let's go back to Newton's second law, which was F equals ma, which could be written as mass times dv dt. And if you remember, we actually found in chapter 9 that that could be defined as, the force could be written as the time derivative of momentum. So if we're using the sort of analogs we've learned, like moment of inertia is the rotational equivalent to inertia. How's rotational kinetic energy related to regular kinetic energy? So we might think, okay, hey, torque is like the rotational equivalent to force, and what we just learned about angular momentum is the rotational equivalent to momentum. So is it true that torque is equal to the time rate change of angular momentum? So let's see. So again, if we start off here, again, I'm just going to write m force equals m dv dt. And in order to make it into a torque, I'm going to cross this whole equation with r. So on the left-hand side, I get r cross f, and on the right-hand side, I get r cross m dv dt. Now the left-hand side is definitely the definition of torque. And what we're asking here, is this the time rate change of angular momentum? I don't know. Let's see. So we have L is equal to R cross MV. Then let's take the time derivative of this. We have to use the product rule. And of course our mass we're going to say is constant. So this ends up to be dr dt cross mv plus r cross dv dt. So it's getting messy. Let me get over here. So I had that dl dt was equal to dr dt cross mv plus r cross m dv dt. So this is what we got so far. Now, dr dt is just v. But v cross mv is 0 because these are parallel vectors. And when you have vectors that are in the same direction, their cross product is 0. So we did find that dl dt can be written as r cross m dv dt. And this is what we had said before. We were saying we had found the result that torque could be written as r cross m dv dt. And what we had asked was, is this equal to the derivative of angular momentum with respect to time, and we found that indeed it is. So basically, what we're saying is we have shown that you can write torque and relate it to the derivative of angular momentum with respect to time. So it is true. That is the relationship between angular momentum and torque. So we have one more equation that we can add to our stable of things that were true about rotational quantities compared to translational quantities. Now, so far when we've been talking about angular momentum, we've been talking about point masses, but we would like to look at the angular momentum of a rigid body. And so what we're doing here is we have this very odd-shaped object, and it's spinning around its axis. And what we're going to do is we're going to find its total angular momentum by finding the angular momentum of every little piece. So we've taken it and we took a little box right here, and it has a delta m, and it's moving at a certain velocity because of its distance away from the axis of rotation, because the whole thing is spinning. So L sub I is equal to R sub I cross with M delta M sub I V sub I. The idea that the entire angular momentum would be found by taking the summation of all these individual angular momenta. So if we took the angular momentum of all the little individual pieces and added them up, we'd get the total angular momentum of the entire object. Now, when we are doing this, this essentially has R sub I, M sub I, V sub I times the sine of theta sub I. And this time what we're going to do is we're going to put that angle with theta sub I, and this R sub I right here can be written as R sub I sine theta sub I. So we're going to say that angular momentum, the magnitude of that, can be written as R sub I delta M sub I V sub I. So we're just talking about what is the angular momentum of that little piece of mass. And we're going to, if we add them all up, we will get the total angular momentum. Now, this velocity right here can be written as omega times R sub I. So I'm going to substitute in this R sub I delta M sub I and then R sub I times omega. And now I get omega outside and I get a delta M sub I R sub I squared, which is actually just moment of inertia. So what we have found is this can be written as the total moment of inertia of the rigid body times its angular velocity. And that is how we're going to express the angular momentum for a rigid body. And again, this makes sense if we think about the translational equivalents: momentum, mass, and velocity. And so then when we think of it that way, it makes perfect sense that this is how we would write the angular momentum for a rigid body. Is it's rotational equivalent of mass, which is moment of inertia, and its rotational equivalent of velocity, which is omega. Now, you can see here it's written with vector formats, and it shouldn't have a vector over I, it should be over omega. You can notice that we are using the right-hand rule to denote the direction of the angular momentum. It will be parallel to the vector for omega, and therefore will be along the axis of rotation. All right, so that is our first part of our makeup videos.